Okay, so this is a redo of yesterday's lecture on Monday, November 29th. As I could not record it, I want to make sure you get it out there to everybody. So, generally, here's a problem. We have a crow's foot wrench, basically going to remove a bolt, and we're going to look at the stress on this point right there as we load 24 pounds on this end of the handle of the wrench. Okay, and this is a typical problem that you can see with most ways of trying to integrate complex loading situations to come up with combined stresses. And this leads you to the more circular equations that we need to find the principal stresses and what the maximum shear stress is. So I want to work through this problem and we'll go down through it. And I gave you the given and what I'm looking for over here on the right hand side. And let's get started. Okay, so the very first thing we want to do is figure out our forces. So find all forces. Okay, and with that, I'm looking for my vertical force for the shear. Okay, it's also my F at A, so that's given to us as 24. Okay, 24 pounds. And I want to take you back a little bit here. So if I do a free body diagram for this thing, and this is my 10 inches, okay, and I have a force here that is my F of A. We're going to need a moment here, and we're going to have a vertical shear there, which is why we got 24 pounds, okay, in order to put this thing in balance. And then the moment will be the F of A times 10 inches, but we're not going to need that right now, and I'll explain why here in a little bit. But in order to make this balance out, we got to have those forces. So this goes back to calculating the shear and why we use the term V, basically. All right, so the very first thing I want to do is we're going to find the moment that's actually acting at point at B, basically. So the moment the moment that's acting at H. All right, and just to keep the world straight, so here's our wall. We got a shaft like so, and we got F of A acting back here, but it has to be translated through the 10 inches of 24 pounds. But we're looking for this point right here that's 6 inches down the 3/4 inch shaft. Okay, and that would be H. Alright, so this is going to be the moment that we're interested in is F of A times 6 inches, which is 24 pounds times 6 inches, and that's going to equal 144. Okay, so that's one thing we need. The next bit that's going to deal on this shaft, so that was basically the bending of this thing, let's put it in red, the bending of this thing this way, alright, that's going to cause that. But the next piece we're going to deal with is we're going to have a torque here. So that was our moment, and we're going to look for a torque here at on that shaft that's going to act on this. So the next piece of this is torque on the 3/4 inch shaft heading to the wall. Okay, that's going to be T. And let's get some underlines under these things so I remember what's going on here. That's going to be equal to my F of A times the 10 inches now, because I am actually looking at this, but based on this distance here. So F of A and 10 inches there. So that's going to put a twist on that, which is my torque. All right. So we get done here. 24 pounds times 10 inches gives us 240 pounds inches. Okay. So there's my torque acting on this, and there's my shaft, or my moment. So we're now literally bending and twisting that shaft from the wall out to B based on these forces. Okay. All right. Next piece of this pie is find the geometry that helps us solve this problem. Okay. So in this, we're going to look for, well, we need to know D, we need to know C, we're going to find I, and we're going to find J. All right. And those are the geometric pieces to our stress equations. And I guess a good place to throw that in now is, remember, normal stress is MC over I, and my shear stress is torque times C over J. All right. So that's why I need C, I, and J. D is a given. That was 3/4 of an inch. But in order to do this, D is equal to 0.75 inches. That means C is equal to D over 2, which gives us 75 inches divided by 2 is 0.375 inches. Okay. So that's our C value. Our I will be based on D to the 4th. Okay. And that'll take care of solving for I. And I'll plug these numbers in. 0.75 inches to the 4th over 64. And if I've done this right, we should wind up with 0.0155 inches to the 4th. And there's probably a few more decimals out there that go with that, but that level is good enough. Find J. This one's going to be pi over 32 d to the 3rd. I'm sorry, d to the 4th. What am I doing? D to the 4th equals pi 0.75 inches again to the 4th over 32, which means our I was half of this, so really our answer comes out to be 0.0311 inches to the 4th. So we're going to need those values down the road. I got C, I got I. Just to make sure I know things, I got M, I got C, I got I got T, I got C, I got J. Should be able to find the normal stress and the shear stress that goes with this problem now. Okay, so let's do this. Nope, pencil, not pen. Find stresses normal and shear. All right, and those will be sigma and tau. We're going to call that tau xy because it's really the whole thing that we're working on here. All right, this will be tau x. That's our normal, and that's our shear. All right, so do shear tau x is equal to mc over I. Plug our numbers in. We had 144 pound-inches times 0.375 inches divided by 0.0155 inches to the fourth, and that gives us an answer of 3,484 pounds per inches squared. And I rounded back. I mean, you got 3483.87, but close enough. Okay. And tau xy will be tau, or torque, times c over j. Remember, j is your polar section modulus, where I was your moment of inertia. And we're looking at 240 pound-inches times 0.375 inches divided by 0.0311. And let me check these numbers, make sure. 240 times 0.375 divided by 0.0311. And I get 2,894 pound-inches squared. Okay, so those I'm going to need. All right, next piece of this pie is, just do it this way. Draw the stress element. And I didn't underline up there either. Draw the stress element. So we're literally looking at this with this being sigma x. We get that. And we're going there, here, there, and there. And that is my tau xy. And I can label those as 2894 pound-inches squared. And this one's going to be 3484 pound-inches squared. Okay, so there's our stress element. Once we get the stress element, we're really setting ourselves up now to go find everything that goes on with this. And we have no, I'll draw it here in red. There is no sigma y, so that's going to be 0. So you don't have to worry about that in here, but I'll just draw it in there because we have nothing, but it shows that there would be something there. And we're going to take a look now at find the resultant stresses. Let's put all the whole word in there. Alright, and that's going to be sigma 1, sigma 2, and tau max. Those are the things we're looking for. Okay? Alright. So, I can do this a couple ways, and I did it yesterday, and I'll do it that way again just to be sure. So sigma 1, sigma 2 is equal to sigma x plus sigma y divided by 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. Okay, and just to remind you, this is the sigma average. We'll go back and do that another way, plus or minus, and this is r, the radius of the part, and r is also known as tau max. Okay, so keep those parts and pieces in mind, and I'll try to do this And we'll do this on 2 levels here, I think. So do this first, and then I'll do the other one. So we're going to plug in our we are sigma x. I lost track of sigma x. 3484 by 2 plus or minus, so that's going to go there. We're going to go 3484 divided by 2. I like keeping the units in things, that way I know things cancel out and the world's a happy place. Plus, and I had 2894. Okay, and when I get done, I'm going to wind up with this equation that'll work. We got 3484 divided by 2 is 1742 pounds inches squared, plus or minus. Let's do this 1742 squared plus 2894 squared equals, and we take the square root of the answer, and we wind up with 3377, and I'm going to make that 3378. Okay, just keep it in the units we're looking at here, inches squared. Okay, alright, so FYI, when we get done, this right here will be tau max, or the radius, and we'll work that out. And this one is our average. That's our sigma average, so we can find the plot the circle. But let's get this solved this way first, then I'll go back and do it the other way. So sigma 1 is equal to 1742 pounds inches squared plus 3378 pounds inches squared equals 5120 pounds inches squared. That's an answer. Sigma 2 is equal to 1742 pounds inches squared minus 3378 pounds inches squared, and that should come out to like 1742 minus 3378, 1636. And that's another answer. And then my tau max will be equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared, which we solved already. All right, and that turns out to be, do that over here, turns out to be 3378 pounds inches squared. Okay, that's our other answer. So that's one method of going at this. The other is to do this. So let's do alternative solution. Okay, sigma average is equal to sigma x plus sigma y over 2 equals the 3484 pounds inches squared plus 0 pound inches squared divided by 2, and that'll give us the 1742 pounds inches squared. Okay, and then I'm going to look for R, which will be the square root of sigma x minus sigma y over 2 squared plus tau xy squared, and that'll be 3484 pounds inches squared divided by 2 squared. Actually, as long as I'm doing this, let's do minus 0, and we'll square that, plus the, where'd the number go? We're looking for 2894. And when I get done with that, I should still come up with 3378 pounds inches squared, and that's that. Okay, and then literally I'm back to sigma 1 is equal to sigma average plus, oh by the way, this is plus minus, plus minus, plus minus. Okay, sigma average plus r gives me that answer, and then sigma 2 is sigma average minus r, and it's going to give me that, and then tau max is equal to r, which gives me that. Okay, so I'm just going to fill in these numbers here. Okay, and they should be negative 16, 36 pound inches squared, and then 5120. Okay, and those are still our solutions, and that's really all there is to this problem, and that's what you need. Now, a little FYI on where this goes. So we now know the torque, the shear stress is maximum at 38, and our maximum principal stress is 51. So what we'd wind up doing is look for a material that can handle these stresses. Okay, so in this one, this could be a simple, they're not really high stresses. We can get away with some, maybe 1020 steel, and at 3/4 of an inch, it'll handle that. Okay, and that's how we wind up doing that. So this part down here becomes future design courses. Okay, and that's really what strength materials get you ready for. And that is, my friends, the solution that I did yesterday in class, and probably a whole lot shorter time than writing it all on the board. But hope you enjoy this. The only thing I think I said yesterday was if I was playing around with a shaft that was hollow, like so, my I is pi over 64 d outer to the fourth minus d inner to the fourth, and then J is pi over 32 d outer to the fourth minus d inner to the fourth. So that might come in handy someplace down the road here, so you might want to keep that in mind. And then simply, it's a nice comparison, is if I make that a hollow shaft, can I make it lighter and still have the same strength, or does it fail in that point if I pick a piece of steel? Alright, so that's how we change designs around a little bit. We come up with different ways to do things. So in essence, that's your answer to the life, and hope you enjoyed this little review of this lecture and a copy of what was going on. Talk to you tomorrow in class. Bye.